angular displacement theta. The radius will be same r only. It has moved from position 1 to position 2. Now, okay, shall we call this as arc length, where S is called as arc length. So usually arc length, this is like a distance, no? It can be centimeter, meter, depending upon R if it is in meter, S will be in meter. R in centimeter, this will be in centimeter. Then, what about theta? Theta is what we say angle. Here I'll call better angular displacement. Theta I'll call this as angular displacement. Is it okay? Fine. So this one. So now if I draw the plane diagram, means let's take like this here. So this is the vertical plane. The particle 1 was here. And after some time, it will reach here. There's a 1, there's a 2. Okay, if you check the other things, so this will be the arc length, no? So this red color, I'll show it. This is the arc length. This will be the arc length, and this will be the theta. Here we do indicate theta. Theta is a angular displacement. You look at the word displacement. So definitely it is having a direction. Whatever the direction of theta is upward. Since we didn't bother in the geometry till now we have studied. And what is the unit for that? Radians. So what is the unit for theta? Theta is expressed in radians here. Of course, we go for degree. That one, there's a very typical one, but the actual unit is what? The radians here, that one. And how one more unit, what degree is what we use basically in geometry. So 2 pi radians is equal to 360 degrees, or pi radians is equal to 2 pi radians equal to 360 360 degrees or simplest thing, pi radian equal to 180 degrees. So like this we can write or I'll write it. This will be 360 degrees. Degree we indicate like this, or pi radian equal to 180 degrees here. The direction, what is this red color arrow? Don't show theta. It is understood. Theta we do measure. In geometry till now, we didn't bother to get the direction of theta. Just only what is this arrow? This will give the sense of rotation. Means curl your fingers. So take like this. This thumb will give the direction of theta, whereas this is the sense of rotation. So how you measure theta? Theta you're going to measure in say some clockwise or anti-clockwise. So here I'll be theta. Theta will be anti-clockwise. So you curl it. Already we have seen in right hand screw rule, no? The similar method. Curl in the direction of curl your fingers in the direction of theta. Open the thumb. The thumb will give the direction of what happened, the theta here. This is only the sense of measurement. Better I call. What we have is this is only the sense of measurement. The theta will be directed perpendicular to plane in which you are measuring. You can see here now. Theta will measure like this. The theta will be directed along the axis. This is called like a axis. Then if you see like a theta very small, so tan theta, we can write it as almost, if theta is very small, so tan theta will become S by R. If theta very small, S equal to r theta. So like this, what we say is like how that arc length related to angular displacement given by this particular formula. I think already you know in the basics of geometry you have come across. So here only I'll give that one. If theta is very small, tan theta equal to S by R. Of course, I know that, but here in the diagram it appears big S, or theta appears little bit larger. So theta is equal to 0.001k straight line. Is related. How the arc length is equal to r theta. I'll switch out the video. Now okay. Can you hear me?
Yes, sir.
Is it okay?
Yes, sir.
Okay, sir.
Yeah, that one. Yeah. Okay, this will be S equal to r theta. We'll get a condition like this. This one. Okay, now, so I think this is something very important. So what is this red color arrow? This will give direction of theta. So theta usually we express in radians. Okay, now let's do one thing. So this particular particle will take some time to move from 1 to 2. No, in that what happen, it will cover an r distance s. So shall we differentiate this? If I differentiate this, ds by dt, let r be the constant. So this will become d theta by dt. So what is ds by dt? This will called as linear speed. D theta by dt. This is called like a angular velocity. So how to define angular velocity? Angular velocity is equal to rate of change of angular displacement, where we write it as omega equal to d theta by dt. So this the symbol. So what is it? This unit for this? Radians per second. So how how we'll call this as? We'll call this as linear velocity. Linear will be directed along one specific straight line. And what about omega? This angular velocity will be directed along the axis. So here, this angular velocity. How to, sir, what about the directions? How v and omega will be? So let me take the when the particle is moving and this is the axis. This is the radius. This is the radius vector. And I'll call this as axis here. Axis of about that axis it will be rotating. Okay, now what is this? This value is r. What about omega? The in the vector form, the v is given by v equal to omega cross r bar. There is a vector relationship. So now based on this, I can show that now the omega will be directed perpendicular to, or say along the axis. It is theta very small. I just assumed theta. So even this is r, tan theta equal to s by r. Even if you want to make it this r, no problem. Tan theta is what? S by r I'll define. So v equal to omega cross r bar. Already I think you have come across high school geometry, no? These things, nothing. Arc length equal to what? R into theta. The relation between the linear velocity and the angular velocity here. So the direction of omega will be, it's an axial vector. So what is the angular velocity? It's like an axial vector. It will be directed along the axis. This is very important. Now, how the vector relationship omega cross r bar. It's given by omega cross r bar. So now curl the fingers here. This is vector form in a simple like a mathematical things. Suppose say we know that particle it moves in a. So how the omega will be directed? Omega will be directed out of the plane here. The omega will be directed out of the plane. If the particle moves in a clockwise, so how the omega will be directed here? Omega will be directed into the plane. This is r bar. This r bar. So sense of rotation. So in so shall I say particle is moving in counterclockwise. Particle is moving in. This will be clockwise. This will be counter clockwise. What about the omega? Omega will be here out of the plane. So here I'll go for these symbols. Very helpful for us. This will be direction into the plane. If I put a circle and dot like this is considered out of the plane. So what is the direction of omega here now? Omega will be out of the plane. Here omega will be into the plane. Sometimes if you get a plane diagram, if you get a 3D diagram like this, take help of this formula. If the plane diagram, no, clockwise and anti-clockwise, just curl your fingers. Curl your fingers, then the thumb will give the direction of omega. Curl your fingers in the direction of motion, in the direction of sense of rotation. So in the books, what happened? So rather than showing like this, no, they have shown sense of rotation. It's nothing wrong. This arrow is what? Sense of rotation. Arrow, this green color arrow is not direction of omega. It's only a sense of rotation. So what is this arrow indicates? Counterclockwise. I'll put it like this. This will be much easier for you. So what is that arrow? Arrow is what? The green color arrow is sense of rotation, not direction of omega. Direction of omega, omega will be directed. Omega will be directed perpendicular to plane containing like a R and V. You can check it here now. Or how V will be perpendicular to plane containing omega and R. Vector cross product. If you can recollect, so what is the direction of V will be perpendicular to plane containing omega and R. So your right hand, you can curl it, you can check it now. In both the cases, you can check omega. You can check the V, you can verify the V. Omega cross R. So put your fingers from towards omega, then curl towards R bar. The thumb will be along V bar. Go this, curl it, all of you curl it once. You have to right hand screw rule. Take help of right hand. Plane diagram, go for right hand screw rule. 3D diagram, go for the vector notation. Okay, fine. So this is about the two velocities what I introduced. Now, sir, what is this omega? I'll call instantaneous angular velocity. Average angular velocity, how you define? Average angular velocity, which is very less we use. So let me define that also. Average angular velocity. This will become angular displacement by time taken. So how we define this? This will become omega average equal to delta theta by delta. I think this is similar to average speed. Can you recollect? This is similar to the average period. So this may not be very important for us, just have an idea, because maximum will focus on the angular velocity, or there's nothing but instantaneous angular velocity. Whenever I say angular velocity means it's a instantaneous only. Okay, got this? So the direction of theta is very important. The omega will be directed in the direction of theta. Okay, now you see that usually what we prefer the vector notation. No? The vector notation means something we maximum give priority for the vector notation. Means everything in the vector form. But here, if I go for vector form, what is the problem I'm going to encounter? I'm just showing complete what all we discussed. This is the no. From here, what this is about the only the basic idea of the linear velocity and angular velocity. Now, whenever I discuss some circular motion, so definitely I'll be taking help of I cap, J cap, because what is the best way of describing a vector quantity? Because omega is a vector quantity, R bar is a vector quantity, and look at V bar. All three quantities, they are vector, no? And they're having direction. So it's always suggestible to go for the unit vectors. But what is the problem here? Unit vector. As the particle goes round, or you can see from here, as the particle goes round, what will happen to R bar vector? Is it a constant? Yes, the magnitude is constant, but what about the direction? Is varying. And look at the V bar. As long as R and omega are constant, it's no problem. But look at the direction of V bar. It's also changing, no? So it'll be very difficult to express the circular motion in terms of unit vectors. First of all, you can ask questions of why you are bringing unit vectors, because look at the angular velocity, position vector, and the linear velocity. They are vectors. So they are vectors means they are having a direction. So can I take help of unit vectors? The answer is may not be, means will not be very convenient, because particle is continuously moving. And what happened to the direction of R bar? R is constant, magnitude is constant, direction is varying. V is constant, but the direction is varying. Magnitude is constant, but the direction is varying. So at one instant, particle is here. After some time, it will come here. Or look at this particular thing. Here, it will be along J cap. After this, minus I cap, minus J cap, plus I cap. And somewhere here at position 2, the unit vector should be around minus I cap, J cap, no? Somewhere in that direction. So taking help of unit vectors, what happened? Little bit troublesome here. I cap, J cap, K cap. Therefore, I must go for some convenient method of expressing the direction also. So here, if you look at what are the two possible foremost directions are. One, shall I say something tangential, because the particle moves in a circular path. Then I'll assume a direction, I'll draw a tangent to the circle. So that will give the direction. So at point 1, how the velocity of particle will be along the tangent. At point 2, how the velocity of particle along 2. So next what happened, we have encountered a problem. What is that? As the quantities are vector, so how to express them in vector form?
Sir,
Uh,
sir,
yes, yeah.
sir. Here we are assuming that theta is very small, no, sir.
Yes, yeah.
Then can't we say that unit vector is almost the same?
No. Just listen for what I'm telling. Don't assume whatever you want. Don't assume unnecessary things. Okay, there's a point 1. Okay, let this be the point 2. So I want this is R bar. This is R bar vector. R1 bar, R2 bar. Of course, magnitude is same. Similarly, look at the velocity vector. Velocity vector, this will be V1 bar, V2 bar. And V1, V2 equal to V, and this is R. So what about the omega? Omega will be out of the plane. Is that okay? No. So these are things are there. But you look at the V1 bar, V2 bar. V1 bar is R1 bar is not equal to R bar. V1 bar is not equal to V bar. This is a very important parameter that is taking place. Okay, got this? So here, how to get the V1 bar? Just draw a tangent. So here, what is the method actually? You have to draw a tangent. What do you mean by tangent? Okay, at point 1, you draw a tangent. Similarly, at point 2, you draw a tangent. Then along the tangent, now pick the velocity V1. Okay, got this? So what is the method we have to follow here? Draw a tangent, then the velocity, linear velocity will be directed parallel or say along the tangent here. What about the position vector? Along the radial direction. So I think there are some two important things are there. What are two important things? One, radial direction. Another is tangential. What do you mean radial direction? Along radial, so we say radius, this is a radius, so this particular direction is called as radial. So when it comes circular motion, the two foremost important directions are there. So one is the tangential, another is the radial. So this will be the tangential, and this will be the radial. And the directions itself, I'll give the name. I think rather than going for I cap, J cap, this will be a better idea. So this particular called as tangential direction. Tangential direction, and this is called as radial direction. Okay, fine. This is so then unit vector directed along tangential direction. I'll call E theta cap. E theta or any of the thing that one. So here there's a typical symbol what that is used in the book. So therefore I'll call this as E theta cap. It's a unit vector. Huh? Then the unit vector directed along radial direction. This will be ER cap. Uh, in the books, what will happen? They called this as normal, En cap, normal to the tangent. And this, what happened? They took T. Instead of theta, no, they took T. So any of the symbols, we can put it here. So what is E theta cap now? We'll define it. E theta cap, it's a unit vector directed along the tangent to the path. What about En cap? It's a unit vector directed along the radial direction. Tangential direction, radial direction. So like this is what we define it. So what is the distance? This is R. Let this be theta. This will be theta. What is the magnitude? As they are unit vectors, so what should be the magnitude of them? Should be equal to 1. Because they're just brought here for what purpose? Only to indicate direction. If the particle revolves in clockwise, then how E theta cap will be in this direction. If the particle revolves in counterclockwise, then E theta cap will be like this. If particle revolves in clockwise, E theta cap will be in this direction. But the radial direction is only one. Suppose since are any quantity directed towards the center, I'll write minus En cap. I think it's okay, no? So this can be positive, or unit vector can be positive, negative. If the En cap positive, if any quantity plus En cap means directed radially outward. If any quantity minus En cap is directed radially inward. If any quantity plus E theta cap. So it is that you assumed in this direction positive. So it will be in this direction. If you get negative, opposite to what you assume. Similar to I cap and minus K cap. I cap and minus I cap. The similar condition what we put it here. Okay, now what we are going to do is we are going to learn now the circular motion using this unit vectors. We'll try to get all the types of different quantities which are available. Okay, fine, this one. So I'll go for the, once again, the basic kinematics, what we had, S equal to only direction change, no, the magnitude remains same. So therefore, the magnitudes V1 equal to V2. But what about the velocity vectors? It should be different. That's all here. Because the directions at 1 and 2 are different, no? If you think in terms of like a unit vectors here. Okay, let's go for the, what we have is S equal to R theta. I'll differentiate this ds by dt r into d theta. Even r also variable for some type of motion. Time being, let me assume that it's a circular motion of constant radius. So ds by dt, this will become linear speed. We know it here. Okay, clear this? So now what is V? V is a ds by dt. This is called like a linear speed. And what about omega? Omega is called as a d theta by dt. So if I differentiate again, I'll get this as tangential acceleration. This I'll write it symbol we use, no? V theta. No. I'll differentiate again. So what do I get? I'll get the tangential acceleration, which is equal to r d omega by dt. So further, what is d omega by dt? What is a theta? Is called a linear acceleration. This is called as angular acceleration. So linear this is called as angular acceleration. So how we define angular acceleration? Rate of change of angular velocity, similar to the basic thing, the what we studied in basics of rate of change of angular velocity. So alpha is equal to d omega by theta. It's also a vector quantity. What is a theta? A theta is called like a linear acceleration or tangential acceleration. Just you should be get familiarized with these things. Okay, let's do one thing. If particle moves in a circular path, so let's see that all, if the speed of particle keeps on increases, then what conditions will come. So this is the R bar. The velocity of particle will be directed tangential to the thing. So it will be V like this. This is R. What about the V? This will be, when it comes here, it is V1. After at other position, what the velocity of particle will be? Let it be V2. I'll say that V2 greater than V1. Then what about the omega? Omega will be directed like this. Here what will happen? We'll get even the tangential acceleration. And omega 1 will be directed like this. Or I'll just write only omega. We know V1 is varying. So actually it should be omega 1 and omega 2. And if rate of change of angular velocity is constant, then alpha will be constant. So how alpha and omega will be in the same direction if the speed of particle increases. So actually we should write like this: V1 equal to R omega, V2 equal to R. If I show 2 omega, you'll get confused. I'm just writing the angular velocity and it's a variable. So what is omega? Omega is in fact is variable here. So what about alpha? Alpha is also again an axial vector. It's a vector. Alpha is angular axis. It's a vector, and I will be directed along the axis. So when speed of particle increases in circular motion, so how alpha and omega will be in same direction. Similarly, if speed of particle there's a separate condition. No, let me take another one. Okay, here let me do one thing. So the speed of particle is going to decrease. So this is the one position, this other position. So let this be the position 1. This is V1. This is V2. And I'm going to say that V2 less than V1, second case. And this is R. Now this is the axis. What about the omega? As we know, as we know already that omega will be directed like this. Curl fingers from like a point position 1 to position 2. Curl fingers from position 1 to 2. Like this. Curl it clockwise into the plane of notebook. No, curl it clockwise. Then the thumb will point into the plane of the notebook. So this will be omega. This is omega. What about alpha? Because say I can, okay, so some of you are getting confusion. Why you changed omega? Okay, I'll do one thing. Just for your help, I'll put like this. Let this be the 1. I say that V2 less than V1, and this will be much easier for you. What's happening here? How the omega is upward only. Anybody can you say about alpha? Alpha should be directed downward. It's a retardation, no? Both will be directed along the axis only. So here, so shall I say particle speeding up, particle speeding up here, particle speeding down. So if the speed of particle increases, then omega will also increase. And if the omega increases at a constant rate, then we can say, we can define angular acceleration and how that alpha will be in the direction of omega. If the speed of particle decreases, then the omega, okay, as it is moving in specific direction, omega will be vertically up. What about alpha? Alpha, now it's a retardation. Speed of particle is decreasing, it's retardation. So how alpha should be opposite to omega. That's similar to what in kinematics. If speed of particle increases, then A will be in the direction of B. If the speed of particle decreases, then we say retardation. How A will be? Linear acceleration, opposite to velocity. Same thing here also. But omega and alpha both are axial vectors. They must be along the axis only. Time being, the examples what I have taken is of this kind. And omega and alpha need not be in same direction for some two-dimensional circular motion. That in the end of this chapter I'll be discussing. We are going to discuss one-dimensional, two-dimensional, and three-dimensional circular motion. First, we'll focus on one-dimensional. Once we get a clarity, then we'll go for two-dimensional and three-dimensional. Okay, I just introduced the angular acceleration also. What should be the unit for this? Radians per second square. This will be the unit for angular acceleration. Both omega and alpha are, so what they are? Axial vectors. already we defined in vector chapter, no? They're like axial vector. Okay, this is about the basic introduction part of the basic circular motion. So why we have to go for tangential unit vector, normal unit vector, and what are the different quantities. So let's go for a general planar motion of circular motion. This will be like a book open, they just directly wrote formulas. So, but as we proceed to the higher level problems, no, the mathematical way of analyzing will be very important. So therefore, I'm just keeping the future numericals. I'll prefer the mathematical way, that one. Books open theoretically just they brought formulas. What all I discussed till now, it's available in book. They brought some relationship between them and ended up. But when you get into the numericals, no, will be very problematic for you with this approach.